Imagine a massive tug of war. Okay. But it's not just two teams pulling hard.
Right.
It's this constant chaotic pull from both sides, yet the rope, well, it never actually moves. It just stays perfectly still right in the middle.
That's a really great analogy. It's a good way to start thinking about equilibrium in chemistry.
Exactly. It's that precise balance where opposing forces are equal, leading to no net change you can actually see.
Precisely. On the macroscopic level,
Oh,
anyway.
and today we're doing a deep dive into chemical equilibrium. This is such a foundational concept in general chemistry.
Absolutely essential. You really can't understand countless reactions without grasping equilibrium. Things happening all around us.
Totally. From big industrial processes right down to, what's happening inside your own body.
Mhm.
So we've pulled insights from a top general chemistry textbook, Chemistry, Atoms First by Burge and Overby, and also some corresponding lecture slides.
Yeah, good stuff. And our mission today is really to distill the most important nuggets of knowledge from these sources, give you a shortcut to being well informed.
We want to connect the dots, maybe find some surprising facts, and definitely show you the practical side, how relevant this chemistry is to your world.
Right. Let's make it stick.
So let's unpack this core concept first.
Yeah.
Dynamic equilibrium. Most people, when they first learn about reactions, they kind of think they just start with reactants and go all the way to products.
Yeah, the classic goes to completion idea. A goes to B, and that's it.
But you're saying that's not always the case.
That's right. Very often, reactions don't simply finish. Instead, they reach a point where you've got a mixture of both reactants and products. And it looks like the reaction just stopped.
Okay, but it hasn't really stopped.
No, and that's where the term dynamic is so important. It just looks static.
Tell us more about that. Is there a good example we can picture?
Sure. Think about dinitrogen tetroxide, N2O4. It's a colorless gas. When it decomposes, it forms nitrogen dioxide, NO2, which is this distinct brown gas.
Right, I've seen pictures of that one.
So if you put pure, colorless N2O4 in a flask, it starts turning brown as the NO2 forms.
Makes sense.
But here's the thing. The color doesn't just keep getting darker and darker and darker until it's like black. It reaches a certain steady brown intensity, and then it just stays that way.
So that's the point where it looks like it stopped.
Exactly. And this is often where students might think, okay, reaction's over, but it's not.
So what's really happening? Why is it dynamic?
Because the decomposition of N2O4 into NO2, it's a reversible process. Those brown NO2 molecules can actually react with each other to form N2O4 again.
Oh, okay. Going both ways.
Precisely. Equilibrium is reached when the rate of the forward reaction, that's N2O4 becoming NO2, becomes exactly equal to the rate of the reverse reaction, where NO2 is going back to N2O4.
So the reactions themselves are still churning away constantly.
Constantly. Forward and reverse, both happening. It's just that they're happening at the same speed, so there's no net change in the amounts, the concentrations of N2O4 or NO2 over time.
Got it. So it's like our tug of war again, both sides pulling equally hard. Or you mentioned an escalator.
Yeah, like a crowded escalator. People are moving up, people are moving down, but the number of people on the first floor and the second floor stays the same.
Okay, that helps visualize it. The individual molecules are active, but the overall picture, the concentrations we measure, they're constant.
That's the essence of dynamic equilibrium. And what's really insightful, and sometimes a bit tricky for students, is that you can reach this same equilibrium state no matter where you start.
What do you mean?
You can start with only reactants, like pure N2O4. You can start with only products, pure NO2. Or you can start with any old mixture of the two.
And you end up at the same place.
You end up with the same final equilibrium concentrations, assuming the temperature is the same. The system finds its balance point regardless of the starting line.
That is a point that often trips people up. It feels a bit counterintuitive.
It does, but it really highlights that the system is driven towards this specific balance state, its most stable state under those conditions. The path might be different, but the destination is fixed for a given temperature.
Okay, so we get the what and the why of equilibrium, this dynamic balance, but how do we actually, quantify it? How do we predict how much stuff we'll actually have at the end?
Right. That's where we need some math, some quantitative tools. We start with something called the reaction quotient, usually written as QH.
QC. Okay.
At its heart, QC is basically that ratio you probably remember. Product concentrations on top, reactant concentrations on the bottom.
Right, products over reactants.
And crucially, each concentration is raised to a power equal to its coefficient, its stoichiometric number, in the balanced chemical equation.
Got it. So it's a snapshot.
Exactly. QC tells you where the reaction stands at any given moment. It's like taking a picture of the concentration ratio right now.
And the key part is at equilibrium.
Yes. The crucial part is that at equilibrium, this reaction quotient, QC, settles into a constant value. And that value is what we call the equilibrium constant, KCK.
Kc, okay, so Kc is the current state. Kc is the equilibrium state.
Precisely. This relationship is often called the law of mass action. And the size of Kc, its magnitude, tells us an enormous amount.
How so? What does a big Kc mean versus a small one?
Well, if Kc is very large, let's say, generally bigger than 100 or 10 squared, the reaction essentially goes to completion.
Favors products heavily.
Exactly. The
Okay.
equilibrium mixture will be mostly products. Think about the formation of the silver ammonia complex, AgNH32 plus. Kc is huge, like 1.5 times 10 to the 7th power.
Yeah.
Products are strongly favored. We would say the equilibrium lies to the right.
Okay. And the opposite, a really small Kc.
If Kc is very small, say less than 0.01 or 10 to the minus 2, then the reaction basically doesn't happen to any significant extent.
Favors reactants.
Right. The equilibrium mixture will be almost entirely reactants. A classic example is forming nitric oxide, NO, from nitrogen and oxygen in the air at room temperature. The kerosys is incredibly tiny, something like 4.3 times 10 to the minus 25th power.
Wow, tiny.
Yeah. So very, very little NO forms naturally under those conditions. We say that equilibrium lies to the left.
And I guess if kerosene is somewhere in the middle,
Yep, if Caries is, roughly between 100 and 0.01, then the equilibrium mixture will have significant comparable amounts of both reactants and products. It's a true balance.
okay, that makes sense. Now, something that often comes up and can confuse students is heterogeneous equilibria. Why don't we always include everything in the Karasir expression?
Yes, that's a really important practical point. Heterogeneous means the substances are in different phases, solids, liquids, gases, aqueous solutions all mixed together.
Right.
So these kinds of reactions, only the concentrations of gaseous species and aqueous species actually appear in the equilibrium expression, the Karasy formula.
Why leave out pure solids and liquids?
Because the concentration of a pure solid or a pure liquid is essentially constant. Its density doesn't really change, so its moles per volume stays the same.
Okay, so their concentration doesn't vary during the reaction.
Exactly. So their constant values are essentially just bundled into or incorporated into the numerical value of Kc itself. They don't appear explicitly in the fraction.
So like if you have solid calcium carbonate breaking down into solid calcium oxide and CO2 gas.
KCO3 solid yields CaO solid plus CO2 gas.
Right. The Kc would just be...
Kc just equals the concentration or partial pressure of the CO2 gas. The solids are just left out of the expression. It simplifies things.
It does. That's handy.
And another powerful thing is how Kc changes when you manipulate the chemical equation itself. Follows predictable rules.
Like what?
Well, if you reverse a reaction, the new Kc is just 1 over the original Kc at the reciprocal.
Okay.
If you multiply all the coefficients in an equation by some factor, say by 2, you raise the original Kc to that power, so Kc squared. And if you add two reactions together to get an overall reaction, you multiply their individual Kc values together. It's a very neat, consistent system.
That's useful for combining reaction data. Now, you mentioned partial pressure for the CO2 example. For reactions that only involve gases, we often use Kp instead of Kc, right? Based on pressures.
Exactly. Kp is the equilibrium constant expressed in terms of the partial pressures of the gases rather than their molar concentrations.
Are Kp and Kc related? Or are they totally different?
Oh, they're definitely related. There's a specific equation. Kp feeds equation TAPR, RT, raised to the power of delta N.
Whoa, okay. R is the gas constant, T is temperature. What's delta N?
Delta N is the change in the number of moles of gas in the balance equation. So moles of gaseous products minus moles of gaseous reactants.
Oh, okay. So Kp and Kp are usually different numbers.
Usually different, yes. Unless delta N happens to be 0, meaning you have the same number of moles of gas on both sides of the equation, then Kp equals Kday.
Got it. That makes sense. This all ties into something really fundamental in chemistry, doesn't it? The connection between equilibrium and energy, specifically free energy, Ag.
Absolutely. The magnitude of K, whether it's big or small, is telling us the same thing, fundamentally, as the sign of Ag degrees, the standard free energy change.
How so?
A very large K, meaning products are heavily favored at equilibrium, corresponds to a negative A degrees. And a negative A degree means the reaction is thermodynamically spontaneous under standard conditions. It wants to go towards products.
Okay, big K, negative Ag degree, spontaneous push towards products.
Right. And conversely, a very small K, where reactants are favored, corresponds to a positive Ag degrees. That tells us the reaction is non-spontaneous under standard conditions. The reverse reaction is the one that's spontaneous.
That link is so powerful. You can predict if a reaction is likely to happen just by looking up thermodynamic data, the Ag degrees values.
Exactly. Or you can measure K and calculate Ag degrees.
Oh.
It connects the thermodynamic drive with the actual equilibrium position. It also helps explain why some reactions just don't seem to do much under normal circumstances. Their B degrees is positive, their K is tiny.
So knowing K tells us about equilibrium, knowing Q tells us where we are now. Can we use those together?
Yes. That's one of the most practical uses, predicting the direction a reaction will shift to reach equilibrium. You compare the current state Q to the target state K.
Okay, so how does that work?
If you calculated Q, your current ratio of products to reactants is less than the equilibrium constant K.
Meaning you don't have enough products yet.
Exactly. The ratio is too small. The reaction needs to make more products to reach the equilibrium ratio. So it will shift in the forward direction, left or right.
Makes sense. Making products until Q equals K.
Right. Now, if Q equals K,
You're already there.
you're already at equilibrium. The system is balanced, no net change will occur, rates are equal.
Okay. And the last case, if Q is greater than K.
Then your current ratio of products to reactants is too large. You've sort of overshot the equilibrium mark or started with too many products.
Too much product.
Right. So the reaction needs to shift in the reverse direction, right to left. It will consume some products and make more reactants until that ratio comes back down to the value of K.
That seems incredibly useful, especially if you're trying to control a reaction like in industry.
Absolutely. It tells you which way things will naturally tend to go from any starting point.
Now, you mentioned DDBU earlier for standard conditions, but reactions don't always happen at standard conditions. How does free energy work then?
Ah, excellent point. That brings us to a really crucial equation. G degrees plus RTL and Q.
Okay, G without the little circle. That's the actual free energy change.
That's the actual real-time free energy change under whatever conditions you currently have described by Q. D degrees is the standard value, a reference point. RTL and Q is the correction factor for the non-standard conditions.
And what does the sign of this DG tell us?
The sign of the actual G tells you the actual spontaneity right now. If G is negative, the forward reaction is spontaneous from this point. If J is positive, the reverse reaction is spontaneous from this point.
Wow, so even if AG degrees is positive, meaning unfavorable standard conditions.
Right. Even if AG degrees is positive, if your Q value is small enough, meaning you have very few products initially, that RTLNQ term can be negative enough to make the overall G negative.
So a reaction that's supposed to be non-spontaneous can actually go forward if you set up the starting conditions right.
Precisely. Like removing products as they form, keeping Q very small, it makes the reaction spontaneous under those specific conditions. Conversely, a reaction with a negative G degree can stall or even reverse if you start with a huge amount of products, making Q large and positive, potentially making G positive.
That's really fundamental to controlling reactions. It's not just about the inherent thermodynamics, but also the current concentrations.
Exactly. And think about what happens at equilibrium.
Well, at equilibrium, Q becomes K and there's no net drive, so G must be 0.
Perfect. At equilibrium, AG equals 0 and Q equals K. So that big equation becomes 0 equals 0 plus RTLNK.
Which means AG degrees plus RTLNK.
Bingo. A direct mathematical link between the standard free energy change and the equilibrium constant. You can calculate one from the other. It bridges thermodynamics and equilibrium quantitatively.
Okay, this is making a lot of sense conceptually. Now, the really practical part for, say, a chemistry student, calculating the actual concentrations at equilibrium. You mentioned using K.
Right. This is where the rubber meets the road in terms of problem solving. If you know the equilibrium constant, Kc or Kp, and you know the initial concentrations or pressures you started with, you can figure out exactly what they'll be once equilibrium is reached.
How do you approach that systematically?
The standard method, and usually the best way to organize your thinking, is using an ICE table.
IC, what does that stand for?
Initial, change, and equilibrium. It's just a little table to track the concentrations.
Okay, how does it work?
You start by filling in the initial concentrations of all your reactants and products. Then, in the change row, you define how each concentration changes as the reaction moves towards equilibrium. This is where the stoichiometry comes in. You usually use an unknown X to represent the extent of reaction.
So like if a reactant is consumed, its change is minus X or minus 2X, depending on the coefficient.
Exactly. And for products being formed, it's plus X or plus 2X and so on. Then the equilibrium rho is just the initial concentration plus the change, which might be negative. So you end up with expressions for the equilibrium concentrations, usually in terms of X.
Okay, so you have these expressions for equilibrium concentrations like initial X or initial plus 2X. What next?
You plug those equilibrium expressions, the E rho values, into the equilibrium constant expression, the formula for Kc or Kp.
So you set Kc equal to product's A reactanza using those expressions with X.
Precisely. Now you have an equation where Kc is known and X is the only unknown. You just have to solve that equation for X.
That sounds like it could get algebraically messy sometimes.
It can. Sometimes it leads to a quadratic equation you have to solve using the quadratic formula.
Right.
Other times, though, especially if K is very, very small and you're starting mostly with reactants, you can make a simplifying assumption.
What kind of assumption?
You might assume that X, the amount that reacts, is so small compared to the initial concentration of a reactant that you can ignore it in the denominator. Like if you start with 1 molar reactant and K is 1010, then 1X is basically still 1.
That avoids the quadratic formula. But you have to be careful when you do that.
Absolutely. There are rules of thumb, like checking if X is less than 5% of the initial concentration afterwards. If the assumption isn't valid, you have to go back and solve the quadratic properly. That's a common pitfall for students, knowing when the approximation is okay.
Good tip. And once you've found X,
Once you solve for X, you plug that value back into the E rho expressions to get the actual numerical equilibrium concentrations.
and then it's probably a good idea to check your answer.
Always, always check your work. Plug those calculated equilibrium concentrations back into the QC expression. The value you get should be very, very close to the original Kc or Kp you were given.
Yeah.
If it's not, something went wrong in the calculation.
Right, that's the final sanity check.
Definitely.
Okay, so we understand equilibrium is dynamic. We can quantify it with K, link it to energy with Rij, and even calculate concentrations with ICE tables. But what if we want to mess with the equilibrium? What if we want to force it to make more products, for example?
Now, you're talking about manipulating equilibrium, and the guiding principle here is Le Chatelier's principle.
Ah, yes, Le Chatelier. How does that work again?
It's a really fundamental concept. It states, when a stress is applied to a system at equilibrium, the system will respond by shifting in the direction that minimizes or counteracts the effect of that stress.
So the system kind of pushes back against changes, tries to reestablish balance.
Exactly. Think of it as the system trying to undo whatever change you forced upon it.
Okay, so what kinds of stresses are we talking about?
There are 3 main types: changes in concentration, changes in pressure or volume, and changes in temperature.
Let's break those down. First, concentration changes. Adding or removing stuff.
Right. If you're at equilibrium and you suddenly add more of a reactant.
The system has too much reactant now.
Yep. So to relieve that stress, it will shift to the right, consuming some of the added reactant and making more products.
Okay. And if you remove a product as it's being formed,
If you remove a product, the system wants to replace it. So again, it shifts to the right to make more product.
and the reverse, add product or remove reactant.
Then the system has too much product or not enough reactant. It shifts to the left, consuming product and making more reactant to compensate.
This sounds incredibly useful for chemical engineers.
Oh, absolutely.
Yeah.
Take the Haber process for making ammonia. N2 gas plus 3H2 gas gives 2NH3 gas.
Right. Hugely important industrial reaction.
Industrially, they often continuously remove the ammonia NH3 product as it forms. Why? Because removing the product stresses the equilibrium, and according to Le Chatelier, the system shifts right to make more ammonia, increasing the yield.
Clever. Using the principle to drive the reaction forward.
Exactly. But remember that important point about heterogeneous equilibria.
Solids and liquids.
Right. Changing the amount of a pure solid or pure liquid doesn't actually change its concentration, so it doesn't stress the equilibrium in the same way. Adding more solid KCO3 to that decomposition reaction won't cause a shift. That's another common misconception.
Got it. Okay, stress number 2. Changes in volume or pressure. This mostly affects gases, right?
Primarily affects systems involving gases, yes, because gases are compressible. If you take a system of gases at equilibrium and you decrease the volume of the container,
That increases the pressure, right? Squeezes everything together.
it increases the overall pressure. The stress is increased pressure. How does the system relieve that? By shifting to the side of the reaction that has the smallest total number of moles of gas. Fewer gas molecules mean lower pressure.
Ah, okay. Fewer moles of gas take up less space, effectively lowering the pressure again.
Exactly. So for N2O4 gas going to 2NO2 gas,
That's 1 mole of gas on the left, 2 moles on the right.
right, if you decrease the volume, increase pressure, the equilibrium shifts left towards the N2O4 because that side has fewer moles of gas.
And if you increase the volume, decrease the pressure.
Then the system shifts to the side with the largest number of moles of gas to try and fill that extra space and increase the pressure back up. For N2O4 to 2NO2, increasing the volume shifts it right towards the 2 moles of NO2.
Makes sense. What about adding an inert gas, like argon, that doesn't react? Does that change the pressure?
Good question. Adding an inert gas at constant volume increases the total pressure, yes, but it doesn't change the partial pressures or the concentrations of the reacting gases.
Well, the ratio Q doesn't actually change.
Exactly. Because the reacting gases don't see the inert gas in terms of their own pressures or concentrations, adding an inert gas at constant volume causes no shift in the equilibrium position. It only matters if the volume changes or if you remove one of the reacting gases.
That's a subtle but important distinction. Okay, the last stress, temperature changes. You said this one is unique.
Yes. Changes in concentration or pressure shift the equilibrium position to restore the same Kc value. But changing the temperature actually changes the value of Kc or Kp itself. This is critical.
Okay, so how does temperature affect K?
It depends on whether the reaction is endothermic or exothermic. Remember enthalpy?
Sure. Endothermic absorbs heat, AOH is positive. Exothermic releases heat, AOTH is negative.
Right. So for an endothermic reaction, AO0, you can think of heat as being like a reactant.
Needs heat to go forward.
Exactly. So if you increase the temperature, you're essentially adding a reactant, heat. The system shifts to the right to consume that added heat and make more products. And importantly, the value of Kc increases.
Okay. Increased T for endothermic, shifts right, K gets bigger. And decreasing T.
Decreasing T removes heat, so it shifts left and Kc gets smaller.
Makes sense. Now for exothermic reactions, they Dutch.
Here, heat is released, so you can think of heat as being like a product.
Gives off heat as it goes.
Right. So if you increase the temperature adding heat product, the system shifts left to consume that heat, making more reactants, and this time Kc decreases.
Increased T for exothermic, shifts left, K gets smaller, so decreasing T.
Decreasing temperature, removing heat product, will shift it right, favoring product formation, and Kc will increase.
Wow. So temperature is the only thing that changes the actual equilibrium constant value.
That's the key takeaway. Concentration and pressure changes just shift the position along the equilibrium line defined by K. Temperature changes move the line itself.
Is there a good visual example of this?
Yeah, a classic one involves cobalt complexes. There's an equilibrium between a blue cobalt chloride complex, cobalt-42, and a pink hydrated cobalt complex, Cocols-2O62 plus chlorine. The reaction looks like. Blue complex plus water yields pink complex plus chloride ions plus heat. It's exothermic.
Okay, so heat is a product.
Right. So if you take this solution, which might be purplish at room temp, and you heat it up.
Adding heat product shifts left.
Exactly. It shifts left towards the blue complex. The solution turns distinctly blue when hot.
And if you cool it down in an ice bath.
Removing heat product shifts right. Toward the pink complex, the solution turns pink when cold. It's a really direct visual demonstration of Le Chatelier's principle with temperature changing the equilibrium position and, implicitly, the KGE value.
That's cool. It really brings it to life.
It does. And Le Chatelier's principle isn't just, theory for a chemistry lab. It has really profound real-world consequences, especially when you look at biological systems.
Well, how? Give me an example.
Well, have you ever heard about how certain toxins, like pesticides or heavy metals, tend to accumulate up the food chain? Biomagnification.
Yeah, like DDT in birds or mercury in tuna. How does equilibrium play into that?
It's related to solubility equilibria. Chemists often use something called a partition coefficient, often symbolized Cal. It's basically an equilibrium constant that describes how readily a substance dissolves in fatty tissue, often modeled by octanol, compared to how readily it dissolves in water.
Okay, so it measures preference for fat versus water.
Exactly. Many persistent organic pollutants, like DDT or PCBs, have very high partition coefficients. They are much, much more soluble in fat than in water.
Ah, so they get stored in the fatty tissues of organisms?
Precisely. They partition selectively into the fat. Then when a predator eats that organism, it ingests all that stored toxin, which then partitions into its fatty tissues. This process repeats and concentrates the toxin at higher trophic levels. It's driven by these solubility equilibrium principles.
That's a slightly scary application, but a powerful illustration. What about something inside us?
Absolutely. Think about breathing at high altitudes. The key reaction is oxygen binding to hemoglobin, Hb, in your red blood cells. Hb plus O2 gives HbO2, oxyhemoglobin.
Okay, that equilibrium carries oxygen around our body.
Right. Now, at high altitude, the air is thinner. The partial pressure of oxygen, our O2 reactant concentration, is significantly lower.
Okay, so that's a stress on the equilibrium, lower reactant concentration.
Exactly. According to Le Chatelier, what happens if you decrease a reactant?
The equilibrium shifts
Now-
towards the reactants.
Yes. The equilibrium Hb plus O2 shifts to the left. This means less oxygen binds to hemoglobin, less HbO2 is formed,
Which means less oxygen gets delivered to your tissues.
leading to hypoxia, oxygen deprivation. That's why you feel breathless or lightheaded at high altitude initially.
But people adapt, right? How does the body respond?
Nature's amazing. The body senses this stress of low oxygen. Its response over time is to produce more hemoglobin molecules. It increases the concentration of the Hb reactant.
Yeah, so now you're increasing reactant concentration.
Exactly. Increasing the concentration of Hb, according to Le Chatelier, pushes the equilibrium back to the right, forming more HbO2, even though the O2 concentration is still low.
So the body compensates by changing the amount of hemoglobin to shift the equilibrium back towards oxygen binding.
Precisely. It allows your blood to carry more oxygen overall, adapting you to the lower external oxygen levels. Your body is literally applying Le Chatelier's principle to survive.
That's why athletes train at high altitude or use those hypoxic tents.
That's the idea. Live high, train low, or using tents simulates that low oxygen stress, triggering the body to produce more hemoglobin and red blood cells, which can then enhance oxygen carrying capacity back at sea level.
Fascinating. So even though biological systems are maybe more complex, maybe steady states, rather than true closed system equilibria.
Right, they're open systems, constantly exchanging matter and energy. But the principles of equilibrium and Le Chatelier's still provide powerful insights into how these systems respond to changes. It shows just how fundamental these chemical concepts really are.
Okay, so let's try and wrap this up. We've covered a lot of ground.
We have. It's a big topic.
We started with equilibrium being this dynamic balance, not a static endpoint.
Where forward and reverse reaction rates are equal.
Then we looked at how to quantify it with the reaction quotient Q and the equilibrium constant K.
And how the size of K tells us whether products or reactants are favored.
We touched on leaving solids and liquids out of K, the relationship between Ka and K for gases.
And the crucial link between K and the standard free energy change. Should you agree, connecting equilibrium to spontaneity.
Plus, using Q versus K to predict reaction direction and the full OG equation for non-standard conditions.
Don't forget the practical AC tables for calculating actual equilibrium concentrations.
Right? And finally, Le Chatelier's principle, how systems respond to stress, whether it's changes in concentration, pressure, or temperature.
And remembering that only temperature changes the actual value of K.
It really ties together so much chemistry, from designing industrial processes like ammonia synthesis,
to understanding environmental issues like biomagnification.
and even how our own bodies function, like adapting to high altitude. Chemical equilibrium is constantly at play.
It truly is. It's this invisible tug of war, this constant molecular dance striving for balance that shapes so much of the chemical and biological world. It's not just a static concept in a textbook.
So maybe a final thought for you, our listener. The next time you encounter a chemical process, maybe cooking, maybe thinking about the environment, or even just breathing, don't just see it as one thing turning into another.
Yeah, trying to picture that hidden tug of war. Think about the dynamic balance.
Ask yourself, what forces are really at play here? What's driving this system towards equilibrium? And what might happen if you just nudged it a little bit?